My name is Derek Binding. I'm a student at Full Stack, and today I'm going to be giving a talk on Docker called Docker and You. Maybe you've heard of Docker before today, maybe not. Docker offers a suite of development operation tools that have really spiked in popularity with many major companies in the past several years. Just a handful of some of the major companies I've seen that have adopted Docker into their approach for software development and deployment. You can see here a lot of big companies. This is just a handful. So you're very likely going to be seeing a lot more of Docker in your software engineering career. In fact, you'll probably see many job listings saying that knowing Docker is definitely a plus. So that's why I want to spend some time introducing you to this technology today. So what is Docker? You can see this set of containers on a barge somewhere. According to Docker themselves, they are the world's leading software container platform. So that's pretty neat, right? Right? So what is a container? It's a good question. According to Docker, it's a way to package software in a format that can run isolated on a shared operating system. I don't know if that's helpful, but it's at least one description. This is kind of the core of Docker, so understanding exactly what they're talking about here is going to be really important. So this may be how you feel right now. I'll try and clear it up a little bit. So what is a container really? Here's my attempt at an answer or several answers. It can be described as an abstraction of the interface between a host machine's operating system and the processes running on it. Another way of going at this question is describing containers as a sort of a virtual replica of the interface that your software expects to interact with at runtime, but sort of in a restricted and limited form. A container is basically an isolated environment for a process to run in, and it's supplied with everything that it needs to run. So that includes things like, its executable code and runtime environment, system resources and libraries and tools and settings, and access to network and block I/O and things like that. Another way you could describe containers is sort of as a liaison between the host operating system kernel and this artificially isolated process. So these are all basically getting at the same idea. I'm just hoping that putting it a few different ways might be helpful. So if you're familiar with virtual machines, you might be thinking this sounds kind of like a virtual machine. You're creating an isolated environment in which to run other programs. And it's kind of valid. If you wanted to go to describe it that way, you might run into some opposition from people who use Docker, but ultimately people have found that that's probably just the best analogy for understanding what a container is. It's basically kind of a virtual machine, but not really. So now that we've got at least some inkling of an idea of what we're referring to when we talk about containers, let's talk about why we might want to use containers in our software development operations. One big reason is to avoid having to hear these words or having to utter them yourself. This has sort of been Docker's main claim to fame. Docker containers provide what we can call environment parity. Parity meaning equality or sameness. So here's the problem. Environment disparity. Your code has to run on a lot of different environments throughout the development lifecycle, including development when you're writing your code, when you pass it off to testing or quality assurance, and they stage it for testing, and then when it gets deployed onto a production server. These are all really different environments. And your code has dependencies, lots of them, and your dependencies have dependencies. And mysteriously along the way, somehow things can just break at some point. And that's why you might end up saying something like, that's weird, it was working on my machine. And so debugging these kinds of problems can be really difficult and time consuming when trying to deal with environment differences. So with Docker containers, these containers essentially provide this environment parity or sameness. They provide an environment for code to run in that is identical regardless of the machine it's run on. This helps avoid a whole host of dependency environment related bugs. And this clearly is a big win in developer operations because you save yourself a lot of time. So this might still sound like a virtual machine. You might be wondering, okay, virtual machines essentially provide the same level of environment parity. They also isolate processes contained in them, keeping them from interfacing with the host machine kernel directly. And in fact, virtual machines have been the de facto standard for achieving this kind of solution prior to Docker. So the question is, why has Docker made such a big splash in IT and DevOps if a good solution already existed? So that brings me to the next reason you might want to use Docker or Docker containers is resource efficiency. And here's some graphics trying to get at the difference between how containers and virtual machines relate to their host machine. On the left, you can see virtual machines. They take up a lot of memory. Each virtual machine running on this host machine is in the tens of gigabytes in terms of the space taking up on disk. They take a relatively long time to boot up and shut down. And that's because a virtual machine contains an entire operating system in itself, in addition to all the other programs it needs and that it's holding to run your application. So if you need 3 slightly different environments to run all of your apps services, then you're going to have 3 full operating systems that need to do the typical startup and shutdown process of an actual machine. And if you're running a distributed system with tons of instances of all your app services, you can see the needed disk space adds up really fast. And this tends to involve lots of extra cost for companies because you can only fit so many virtual machines on one piece of hardware, and hardware is not cheap. On the right side, you're going to see that Docker containers, on the other hand, they don't have their own operating system. So they're actually teeny tiny compared to virtual machines in the tens of megabytes. Instead, containers share the host machine's operating system to make system calls and get the resources they need. And this removes an astronomical amount of overhead compared to virtual machines, allowing for much greater data density on the machine. This also allows them to boot up and shut down as fast as any other application you might run on your computer, because that's all a container is. It's just a process, a simple process that you can boot up or shut down. And this results in huge savings because the same huge distributed system that required tons of machinery now requires only a tiny fraction of the hardware it needed with virtual machines. And containers also enable you to perform even more rapid, continuous integration and deployment of fixes and features. It allows you to quickly and cheaply scale your services horizontally, up or down, by starting or stopping new instances of your application simply in a matter of seconds, as opposed to maybe minutes with virtual machines. So virtual machines are just simply much more expensive and tedious to deal with. And this slide, it doesn't really have anything to do with the resource efficiency topic, but I figured while I have this graphic up, I should mention this. What I'm trying to convey here is that Docker also introduces something of a paradigm shift for a lot of software as a service companies who decide to adopt it. Because virtual machines eat up so much disk space, you'd be crazy not to try to fit as much as you can onto each virtual machine to attain that kind of data density. But this constraint that a lot of DevOps teams have faced really incentivizes some poor paradigms for architecting software, basically making it necessary to develop software as a big, complicated, essentially monolithic unit where all the processors are tightly coupled together and difficult to modify individually. That's kind of what I'm trying to get at with the 3 processes pointing at the one virtual machine. Really, you could add a lot more programs to that diagram, however many your software relies on to function. Docker, on the other hand, enables developers to practice much more sustainable, scalable paradigms for developing software. You can see each container gets one process, and this is canonical Docker best practice. one process or service per container, period. You can then design your software as a composition of a bunch of smaller single-purpose services that interact with each other as needed. This makes it a lot easier to reason about your software because everything's doing one thing well. It also makes it much easier to continuously integrate and deploy fixes and features to individual services without having to worry about affecting others. So sorry about this, is a little bit of a tangent, but I think it was worth mentioning. Now, where does this magic come from? How did Docker figure out how to accomplish this super lightweight virtualization method? First, I'll mention that containers and their benefits didn't really originate with Docker. Containers have actually been around for a while, most notably as a utility introduced in the Linux kernel in 2008, aptly named Linux containers, or LXC for short. Linux containers basically do what Docker does, but it's way, way too complicated for the average software engineer to derive any benefit from it, much less a whole team of engineers. The folks at Docker basically figured out how to use Linux containers really, really well, and then abstracted away all the complication and made a really straightforward declarative API for automating this process of creating containers with the software you want running in it. That's basically Docker's big contribution in container technology. Now, how this all works under the hood, I honestly can't tell you in great detail. The low-level details require a lot of knowledge of Linux kernel and its utilities, and I simply don't have that. But if you would like to look into it yourself, I'd say start reading about Linux containers and then something called control groups or C groups, and then namespaces. These are really the basic building blocks of the isolating features of containers. But for now, let's leave it as some magic that we don't understand too well. Now I want to get into a quick how-to, just so we can get into a little more detail and less about this abstract stuff. So let's see how we can get a container up and running. I'll show you what it looks like to get a basic Express server and Postgres database container working together with something called Docker Compose. I'm going to kind of breeze through this because there's a lot of detail and there's not a lot of time. But this is what a Docker configuration file looks like. It's just called a Docker file. It doesn't have any file extension. These are just all of the instructions that you give to Docker saying, here's what I want you to do to build my container. So the from keyword is what starts every Docker file. You tell it the base image. An image is basically the basis of a container. It's kind of like a blueprint constructed during the build process. And so Docker reads this document and executes each command in order to construct an image of what, like a blueprint of what your container will look like when it's booted up as a process. All these keywords do different things. So kind of to walk through what's happening, we're gonna install a Linux distribution of Alpine, which is a really lightweight Linux distribution, and we're gonna install the Node long-term support version onto it. After that happens, we'll make a new directory inside of the container called user app. We'll cd into that directory. We're going to copy our package.json from our source files into the container, and then we're going to run npm install, and it's going to install all of our node modules inside of the container. This volume thing is an important concept to understand with Docker. Here we're specifying that we're going to want to mount a file system from the host machine onto the Docker container. By default, Docker containers are completely enclosed, have really no access to anything outside of them, but and they don't have the ability to persist data beyond their life cycle. So volumes are essentially the solution to persisting data. You enable the container to persist data in a very specified location on the host machine with very limited restricted access. Then, after that happens, we're just going to copy in all of our source code from our program, designate another volume here on our root app directory, and then we're going to expose the port that we're going to be listening for requests from. And these are just some other commands that have use with building Docker files. Now I'm going to switch real quick to my editor. You can see here I've got a web service, Postgres service ready. In here, got a Docker file with essentially the same commands we were just looking at. Postgres has its own Docker file. And interestingly, so this creates a Postgres service, and then I'm copying in a seed file into the init directory that runs whatever files it finds in there. So when this boots up, it's going to seed the database, and then it exposes the typical Postgres port. All right, so here I'm going to show how you run a Docker file to build an image, which is the blueprint for a container. So I've jumped into my directory that has the Docker file in it, and I'm going to run docker build the current directory. Oops, typo. And you can see it's now executing each command in order from in this Docker file, and you're getting some of the output from inside the Docker file where it's installing our node modules right here. And when it's done, it'll just exit the process, and I'll have a blueprint of my container. I'm going to skip this because I've already built this image. And the way you run a container is you say docker container run, and you give it the container name. And you can see your containers. Sorry, docker container. And list all of them if they're not running. Sorry, the Docker, to boot up a container, you have to give it an image to run. So looking at our images, I could say docker container run and then give it the image ID, and it would boot it up. I'm going to skip that and jump to a slightly more useful feature of Docker, and that's Docker Compose. Essentially, booting up multiple containers and getting them to interact with each other. And that's done with something called Docker Compose, and this is a Docker Compose configuration file. There's not time to go through all of these implementation details. But the important points is that I'm mounting volumes from inside the container onto a file system on the host operating system so that my container can persist its files and data. And if I wanted to, I could actually develop from outside the container, inside the container. So to do this, you need to get into the directory with the Docker Compose file and run Docker Compose up, and it'll look for a Docker Compose file in the directory. And this little link directive here is saying, I want the server, this Express server I'm creating, to be networked, to have network access to the Postgres service. And so it'll have access to this port on the Postgres container. You can see all the output logging from inside the server container. Webpack is now compiling the source code for the front end, and then the node server is going to boot up and try to make a connection with the Postgres container. Important thing to know is I don't have Postgres running on my machine currently. So that's kind of how you know Docker's working. If I try to do anything with Postgres right now on my machine, it would give me errors because Postgres is not running, but it is running in this container. So here we go, we've got Postgres and the server are totally connected. We can jump over to localhost 8080, and we'll see a familiar web app author up and running from inside of our Docker containers. And it has full access to the Postgres database so that it can load up users. You can do all of these features. The data in the database will even persist because we've mounted a file system onto it here. So if you didn't do this and you tried to make some read and writes to the database, once you spun down the container and spun it back up, you'd lose all that data. So volumes allow you to persist the data. And I'm not going to demonstrate it, but I created a developer Docker Compose file that you can also run. And it just has one different command, basically running my code in development mode with Webpack watching the front end files and node monitor watching for changes on the back end. And I can boot up Docker Compose, have this app running, and do my normal development process of just working on my code, saving it, updating, refreshing, and seeing the changes live. All of that works with Docker containers because of these volume mounts. And that really sums it up. I wish I could get into more detail because there's a lot of really cool things you can do with Docker. And it's really not that hard to get set up. So I just want to cover the key takeaways really quickly. Concepts of a container being a lightweight, virtualized, isolated, self-sufficient environment for running a process. A Docker file is the config file. You provide all the commands for Docker to execute to build your container image. An image is simply like a cached blueprint for booting up a container. The volume in the config file, in the Docker file, is where you specify a host storage file system mounted to the container in order to persist data beyond the life cycle of that container. And then a Docker Compose and the Docker Compose YML config file is how you compose discrete services in containers together to make a fully functioning application. And the key benefits of Docker is that it provides environment parity from development to testing to deployment, so you don't run into all these weird environment bugs. It is a tiny fraction of the overhead of virtual machines, just teeny, teeny, tiny, so you have much greater data density on your servers. They're extremely portable, and the environment parity speeds up continuous integration and deployment. And it really automates the build process of a developer environment. Imagine just someone handing you a Docker Compose file and you're just booting it up, and instantly you have an entire developer environment that is exactly identical to the production environment. You can just start working on code there instead of having to install all this stuff yourself. So really, really convenient. And that concludes my presentation.